So let's talk about forces. A force is just a lift, a push, or a pull on an object. So it's a lift, a push, or a pull on an object. And a force causes motion. So I have my brick that I'll have to, put back and finish our building activity that me and my dad are working on in the backyard. If I push my brick, use a force, it moves, right? You all see that? Okay. If I just push it, what happens? And then what happens? It stops. Why does it stop? Who can tell me why it stops? Dean? So friction. There's friction between the brick and the table. And friction is a force. And it's a force that resists motion. So with my brick, it was going to the right of the classroom. If friction resists motion, what direction would be the force of friction? Yeah, the other direction, to the left. So it resists motion. It's going to slow things down. There's some things with more friction, some things with less friction. Who here skis or ice skates? Right? You're going down the ski slope, and if you don't stop yourself, do you stop? If you're ice skating, do you stop right away? Now, what if you were just like walking and you just stopped actual walking? Would you stop or keep going? You'd stop, because there's more friction between your feet and the ground than your ice skates and the ice. What if I drop the brick or I drop this roll of tape? What's going to happen? It's going to fall. Why does it fall? Gravity, yeah. So gravity is an attractive force. What does attractive mean? If objects attract each other. Aiden? Yeah, they come together. So it's an attractive force between two objects or masses. It's a force that brings objects together. So it brings us to the earth. Once we get far enough away from a mass, we don't really experience any gravity. The further we get away, the less gravity we have. So, I have my hammer. If I hit something with my hammer, is there a lot of force? Yeah. What if I hit this brick? There'd be a lot of force? What if I hit my hand? It probably hurt. What if I hit my hand really hard? It hurt. How hard would I have to hit this to break the brick?
Very hard.
Really hard. My dad might be a little mad because I'm breaking one of our bricks, but he's going to have to deal with it. So if I put my brick on my hands, how much does my brick put a force on my hands? Yeah. Right? And if I break my brick, how much force am I putting on?
A lot.
It's going to be
A
on
lot.
your brick.
Okay.
It's not going to hurt though.
Why didn't it hurt? Joe?
The brake absorb all of the impact of you trying to hit it.
How'd you know that? That's right.
Because
How were you able to figure that out?
I saw you hit it, it hurt. I don't know.
But how did you know it absorbed all that force? Like,
Because,
The crack.
yeah.
Broke open.
but why didn't it go into my hand? We said there's going to be a lot of force
Because
going into
it's
my hand,
not-
the brick from the brick, and
Hammer
this.
hits the
Stop.
sun or
Because
then they
when you hit something, most of that force gets absorbed, and then sometimes it can break the object. So most of it got absorbed when you hit it, and then the rest got made the brick break, and then it just went the opposite direction, and then it goes down. It just went
Okay.
That would cost
I like that.
the,
Carter?
word.
Yeah.
And those answers are amazing. They're all right. And that's because of Newton's first law of motion, which is the law of inertia. And the law of inertia says that an object in motion will stay in motion, and an object at rest will stay at rest, unless acted on by an outside force. So basically, objects keep doing, or they want to keep doing, whatever they already are doing. So if you drop something, it wants to keep falling, and it'll keep falling until it hits the ground. So the hammer, it's moving, it's got a lot of mass. So inertia is just how much mass, really how much mass an object has. So it's got a lot of inertia. The brick is very massive, so it has a lot of inertia. What, is the brick moving? No, so what does the brick want to do? It wants to stay there, but the hammer wants to do what? Keep moving. But the brick's like, no, I want to stay here. So they kind of cancel out each other, but all that force is now going into the brick, which causes the brick to deform, and it deforms enough and cracks around my hand. So all that force and energy is actually going to the brick and not into my hand. If I just did the hammer on my hand, the inertia of my hand would tell the hammer not to move, but that would hurt a lot. See?
Pretty sure in like third grade we went on a field trip to, I don't remember which college, and then there was a physics thing, and we got like a huge board or and then they
And then
cracked. It was on,
practice
it
in
was
a block
on, it was
over
on
your chest.
O'Neill's bed, I think.
Okay, yeah.
O'Neill's bed. That's
My nail's bed.
how you say it.
So I'll tell you why I don't do that one.
O'Neill's bed.
There was a teacher that had a student take a sledgehammer and do that, but the student missed the brick and hit the teacher. So I decided not to do that, because I know I can not miss a brick on my hand, but having someone else maybe miss
Probably.
with a sledgehammer would hurt me a lot, and I don't want to risk getting hurt. So that's Newton's first law. It just says objects do whatever they're doing. They're sitting still. So Brian's not moving. He doesn't want to move.
Unless he does.
No, we know Brian doesn't want to move. When you're on your couch, you have a lot of inertia, because you don't want to get off your couch or out of bed in the morning.
That's
When you're going down a hill, like if you're going down the stairs, you kind of going to keep going down the stairs until you get to the bottom, because you're already in motion. You have to put a lot of work in to stop yourself. If you start running down a hill, it's a lot of work to like stop halfway down that hill. You have a lot of inertia. You're moving. You want to keep moving. Okay.
So does like the moving force always overpower this force that's staying still?
Doesn't always overpower it, because I could push a force on the brick, and the brick won't move, right? So it will eventually move if I put enough force on it. And we'll talk about that as we go on with our other Newton's laws. So an object at rest tends to stay at rest. So what would happen if this tablecloth this young gentleman is holding is quickly removed from under stationary like glassware and tableware? Think of like his the first law.
I wouldn't move,
Yeah, it wouldn't move. Why wouldn't it move?
because you're pulling it so fast, they don't have time. Like,
Yeah. So if I have my brick and a piece of paper, we'll say it's a tablecloth. Don't have a tablecloth here. If I pull it really quickly, what should the brick do? Stay. Move a little bit. Grab the paper. It's okay. Grab paper now. So,
check this out. I hate to break it to you, but I've seen that before. It's a magic trick. It's not a myth.
This isn't, but there's a video that's been making the rounds on the web that is a twist to this trick that I think is right up our alley.
And that is?
In this clip, a table as long as a bus and set for a banquet has its tablecloth pulled out from under all its settings without disturbing any of them, using only the power of a super souped up motorcycle.
Now you're talking.
Thought you'd like it.
In this viral video, rather than a quick flick of the wrist, it's a quick flick of the accelerator. And abracadabra, the tablecloth disappears, and a perfectly laid table remains. But is this turbocharged trick true, or just special effects sorcery?
All set up? You ready to run Christmas dinner?
I can't wait.
Uncle Jamie always does that. Get started.
Go fast. And they go fast.
Well, some stuff stayed on the table.
Abracadabra that, eh? Despite Jamie gunning the accelerator on the Superbike, it wasn't enough to overcome the friction of 24 table settings.
That tablecloth has to start moving faster from the get-go. It needs more of a big jerk. I'm not talking about Jamie, I'm talking about some sliding in the rope so he gets up to speed and then boink, pulls it out at speed. That's what we gotta do.
As Jamie throttles the throttle, the line unspools and
A little better.
That was so much closer than I thought it would be. Look at that.
It's a little sloppy, but it's a lot better than it was the last time.
I'd say 90% of what we had stayed on the table. I mean, it all got tipped over, but it stayed on the table. That's a lot closer than I thought we'd be.
Well, you know what that means?
What?
I just need to go faster.
I'm not sure if speed is the only fix, but definitely speed will help. How fast do you think we want to go?
100 miles an hour.
You need like a quarter mile to get up to that speed.
Let's go find a quarter mile.
Okay. All right, here we go. Possibly the world's biggest tablecloth pull in 3, 2, 1, go! It's certainly as good as it gets. It's not bad. Not bad at all. Everything slid, especially on the front half. We lost a few place settings. Most everything is still standing, but honestly, you know what I'm thinking?
What?
They faked it.
Yeah, they faked it. It's busted.
Yeah, totally busted.
busted. But on Mythbusters, that can only mean one thing.
That run wasn't half bad. In fact, it was pretty darn good, but it wasn't what we saw in the clip. So that's what we got to do next. We're going to have to fake it.
What's different about this setup than its predecessor? Actually, quite a lot. I started out by treating the entire tablecloth with a dry lubricant made for sailboat sails, and that should actually reduce its coefficient of friction. But most importantly, I then laid down on top of the tablecloth a sheet of plastic, 24 feet long, and mounted at the non-motorcycle end of the table. And then we set the table as normal. What this means is that between all the place settings on the tablecloth is a thin membrane on which everything sits. So the tablecloth should, in theory, slip out easy as you please without disturbing anything on the table. That's how I think they did it. This is tablecloth pull, the cheat. 3, 2, 1, go! And that's how it's done.
Who can tell me why it didn't work perfectly for those first couple trials without cheating? Dean?
Because there's always going to be at least some friction where it's going to pull everything else. So there has to be some.
Yeah, there's so much stuff and so long of a tablecloth. There's some friction there which causes, the first table set to move. With really heavy things and a smaller tablecloth, you can do it. It's got to be like satin or silk with very little friction. I asked my mom if I could try this at Seder dinner on Saturday. She said no. Kind of disappointed. It's a really good Passover trick. Don't ask your parents; they'll say no. I hope. You want to ask and see what they say. You can ask. Ask your parents. We have time. We'll talk about the other assignments some more from yesterday. So an object at rest tends to stay at rest. An object in motion tends to stay in motion. So the crash dummy is not wearing a seatbelt and is moving along with the car. Both the car and the dummy are moving at 100 kilometers per hour. Draw what will happen through Newton's first law. So that image is kind of drawn in for you. And this is a really important concept to understand, especially if you've ever driven in a car. Has anyone not driven in a car before or ridden in a car? Okay. Hopefully no one's ever been in an accident, but if you had, you probably experienced this. So if you're driving, and we talked about this with combining velocities, if the car is moving at 100 kilometers an hour, how fast would you be moving? 100 kilometers an hour. If the car hits something and stops instantaneously, how fast are you moving? 100 kilometers an hour. What prevents you? What's going to happen if you're just sitting there? You're going to fly out forward and hit the windshield and then hit something else. And eventually gravity will bring you down and you'll hit the ground. What keeps you from doing that? The seat belts. So anybody can tell me why we have seat belts? The mom?
So like, this ring for like the indoor seats, if you get into an accident, like, because when the seatbelts, when you pull them out far enough, they don't go anymore. So when that happens, you go over, but you won't go all the way.
Yeah. So think of Newton's first law. We want to stay in motion. The seatbelt will act as that outside force that keeps us from going forward at 100 kilometers an hour. So they have all these seatbelt laws, and the reason why they have the seatbelt laws is because the people who wrote the laws why they need to have seatbelt laws use physics to understand that they're really important. They're going to save your life. So back when my grandmother was a kid, they didn't have seatbelts. And kind of just thinking that in your head, imagine getting into an accident, if you've seen an accident like on TV in the news, without having a seatbelt.
Those cars aren't as fast.
They were pretty quick. I mean, we're going like 200 miles an hour, but you don't really drive 200. They can still go 60 miles an hour. So it was really dangerous. If you got in a crash, you had a lot of potential injury coming from it. So that's why wearing seatbelts is so important, especially when you're driving in any car. They have special seatbelts if you're going really fast, or race car drivers have special seatbelts built. Just like it really holds you in and basically makes you part of the car. So the car stops, you stop. Our seatbelts give us a little bit of give, and we'll talk kind of more about that when we talk about momentum at the end of this unit. So in this example, we have a motorcycle and a brick wall. We have a car and a brick wall. What's going to happen in either of these two instances if they're both moving and hit the wall?
Car guy wearing a seatbelt.
Well, what just happens in general in the storyline?
They crash.
Yeah, they crash. If they're not wearing a seatbelt, then they're going to keep going. So motorcycles, you don't have a seatbelt, so they'd be launched forward over that wall. Car driver's being safe, he's following the law, he's wearing a seatbelt. So he's going to be safe, relatively safe, and held into the car. He's not going to go flying through the windshield. So that's Newton's first law. So the first law says, again, objects in motion stay in motion, objects at rest stay in rest. So you're going to keep doing what you're doing unless something else makes you move or makes you stop. So friction is an outside force that makes everything stop. if you throw a ball or you roll a ball, it eventually stops. You guys play soccer, you kick a ball, eventually rolls and stops in the middle of the field. Friction is that outside force acting on the ball that wants to keep moving forward, that's moving forward, that stops it. You can get the ball moving again if you apply a force by kicking it, but the ball wants to just sit there until you kick it. Give me a thumbs up, thumbs down how we feel about Newton's first law. Good? Awesome. So, what, 10 minutes? So Newton's second law of motion states that the greater the mass of an object, the greater the amount of force is needed to accelerate it. And what did we say acceleration is? So the change in speed over time, very good. So the more mass something has, the more force we have to apply to it to increase its speed. So to get it to move or to slow down, to change its speed. So I have half of my brick, and I pull it. What do I have to apply to get it to start moving? A force. Why do I have to apply a force? Because what does the brick want to do right now? Stay there. Why? First law of motion, that's what it's doing. It wants to stay still. So I have to apply a force. Now if I added the second half to the brick to it, in order to get it moving, what do I have to do? Apply more force. Why do I have to apply more force? It's got more mass.
Inertia to stay there.
Yeah, so it has more mass, it has more inertia, it wants to stay there more, so I have to apply more force to get it to move. If you've ever tried to push a car, who here has tried to like push a car like if they run out of gas? Or have seen it, known anyone who has to push their car like off the side of the road or they run out of gas? Do you guys? It's pretty easy, right?
Definitely. No.
I would say it's not pretty easy.
Super easy.
It's pretty difficult. Why is it so difficult?
Because cars are heavy.
Yeah, cars are heavy. They have a lot of mass.
Isn't it easier because it's like spread out over more length? Like, and it's not like.
It's still got the same amount of mass though. So you still need the same amount of force to move it. Now you can get more people pushing on it because it's spread out than you would if it was like in a little tiny square with that same mass. But it's the same mass, so you still need the same total amount of force. What if we pushed, what if I had Alex push this chair? Yeah. Does he have to put a lot of force to get it to move? Not much. What if I have Dean sit in the chair? So do you think he'll be able to push it as easily? No, why not? Because we added mass. So Dean's pretty muscular, he's got a lot of mass. I saw Dean working out. He benches like 420, I saw him. And by 420 I mean grams, not pounds.
Oh man. Kilograms.
Okay, I wouldn't say kilograms. So, the more mass something has, the more force Alex has to use to push it. If I sat it on the chair, would Alex be able to move me, do you think? Maybe?
I got games.
Come on, Alex.
You got this.
Put your foot on the thing. Yeah.
Why is it harder for Alex to move me?
Because you,
Yeah, I work out even more than Dean, so I have more muscles.
Shots fired. I think I might be more
So he requires more force to push me to get me to accelerate. To go from a zero velocity to some other velocity. Which So the equation for force is mass times acceleration. So circle which cart would be more difficult to push, and then explain it using Newton's second law. Stephanie, which cart would be more difficult to push, require more force? Yeah, the one with all the stuff in it. Why is it gonna be the one with all the stuff in it, Priscilla?
Because it has more mass.
It's got more mass, and we said more mass means you need more force to get to move at the same speed. So just to get me moving, Alex had to put a lot more force than he did with the empty chain. So the greater the force applied to an object of the same mass, what do you think would happen to its speed if we applied more force? Alex? Yeah, it's going to accelerate. And what's the saying that Yoda and Obi-Wan Kenobi say to Luke Skywalker in Star Wars? May the force be with you, but we know force is what?
Mass times acceleration.
So may the mass times acceleration be with you.
Yeah, it doesn't sound as good.
Yeah.
But only certain people will know what you're talking about.
Everyone else is good.
Anyone who watches Star Wars will know what you're talking
So you need everybody.
about. Because they'll know what force is.
But what if they don't know physics, like at all?
Well,
Then they won't.
Then they won't know, and you can teach them.
Exactly.
yeah, you need to. Trust me, the math class teacher has no idea what he's